And we are starting. I'll put it in presentation mode. And here we go. Everyone can see my screen, right?
Right.
Okay, good. All right, so welcome everyone. Here we go. I'm just going to breeze through our initial stuff here just so we can get into our presentations. We've got two nice presentations today, both of which are going to be pretty extensive, I believe. So we want to roll through this intro stuff, which most people I think are pretty familiar with. So as we know, these meetings are every third Thursday. Sorry about that first email I sent out. I said Friday. That was a real boneheaded move. Again, this is just time for us to all check in, and we're supporting groups who are working in the Delaware River Watershed Initiative, but also folks that are just in the Delaware Basin. Stroud Center is supporting this via DRWI and Seesaw. This is the website. Feel free to go in here and look at the info. 4 states, 1 source. It's the Delaware River Watershed Initiative site. This is the William Penn Foundation funded grant. So these are just our goals. You know, this is certainly time for anyone to ask questions, whether you're new to the situation or whether you've been around a long time. Feel free to, you know, ask the group questions, network, whatever. We're having station owner manager presentations. Francis Collins, as I mentioned, is doing his today from the Primrose Creek Watershed Association. And John Jackson is doing the focus topic presentation, part 2 of conductivity. And I'll have some updates from the Stroud Center. So here's the facilitators, me, Rachel, Krista, Shannon from the Stroud Center, and Carol Armstrong and George Seeds, Master Watershed Stewards. This meeting is being recorded. Please just keep your microphones muted unless you're gonna talk. Recordings are available. So, you know, feel free to, if you need anyone from your group to see this or whatever, feel free to, you know, put them in touch with those recordings. So here's our agenda for today. As I mentioned, Francis is going to be talking about stuff going on in the Primrose Creek watershed. A lot of wacky stuff happening there. John's doing part 2 of his conductivity presentation, and I'm going to do some polls at the end. I hope that's okay. I sent out a poll with the recent email, and we got some responses on that. So thanks to everyone who did that. And I'm going to do some additional polls today. This is just sort of our way to check in on the efficacy of these meetings and such. So, you know, just to review, primary goal of this Stroud support to folks is Stroud support on this network is to station owners and, you know, to support station owners and managers and volunteers in using the stations for their own purposes, looking at local conditions and answering local research questions. Secondarily, we're doing internal data analysis and developing some methods to characterize watersheds based on the data. Here's this link. We haven't had much response for photos of the month or just sharing photos, but feel free to use this if you'd like. I included this in the one reminder email. Other updates here. This is a workshop that's happening February 9th to 10th. You see, this is the second round of this building workshop in which attendees over the course of 2 days build a CTD monitoring station. So you buy a monitoring kit and a CTD sensor and a battery, and basically program and assemble that in the workshop. Register by December 31st. We have a few spots still open. So just go to this website. It's also listed on the Stroud Center events website as well. Another event to mention, Journey from River to Faucet, how collaboration between states ensures adequate drinking water supply across the Delaware Basin. This is on January 13th. And actually, I'm sorry, this is the wrong address. This is on the Stroud Center events site. So just go to Stroud Center and check out events and it'll be there. Another update, we're working on this dissolved oxygen probe for incorporating into the monitoring stations. There's a few stations out there that do have a DO probe. It's pretty expensive, about $3,000. So there's hasn't been much on that in that direction. But this sensor is about half the price, and Sarah Damiano at Stroud is working on, kind of testing this sensor out. So that may be available sometime. Again, I've mentioned this a couple times, but this is a special charger that Shannon kind of rigs up for charging station batteries, but it's nice because it gives you a readout. So if you'd like one of these, we have some available. You can just be in touch with us. And then I think we're ready to move on to Francis's presentation, unless we have any questions. Any questions at this point? All good? Okay. Francis, if you want to share your screen and proceed with your presentation, we can go ahead with that.
Okay. Well, okay. Is everything coming through? Is there a bunch of happy people on the screen?
Bunch of happy people. And actually, Francis, I realized I forgot to show your intro slide, so please introduce yourself.
No problem. Francis Collins, I'm the guy that should have his mouth closed here, so that's me back there. And I am a board member of the Primrose Creek Watershed Association in Solebury Township, Bucks County, near New Hope. And I'm excited to share 4 events that our sensors recorded that are helping us understand what is accelerating dry periods and dangerous times along our watershed. Now, I'm not going to read everything that's on screen, so I'll let you scan, but essentially, the big question here is, where did the bugs go? We work with 2 schools, and we do the PTI indexing twice a year. And the kids back in the day when you went to school, really enjoyed getting out of school and getting down to the creek. This group just walks, it's on their campus and makes it real easy. This is the Solebury School. The other group is the public school in the area, the New Hope Solebury School District High School. And we had a near miss with that, and it's something I'll point out a little later. But as you can see, Phyllis, who's this cute, wonderful teacher here, basically said, number 1, the bugs are dying. We were getting terrible measurements, and then the creek was going dry. And the kids asked questions about safety and risk. And I'm going to cover our monitoring with the bad guy in the whole group, a quarry that's smack dab in the middle of our run. So our storybook characters are on the left, taken from Pennsylvania Geological Survey magazine. And we're going to be talking about water, carbon dioxide, carbonic acid, the Old Man Mountain, and the bubbling. But we've had 2 pirating or swallow-holing in 20 months. And really, everybody's talking about safety. We know these things happen naturally. We're not, when we talk about the caves of Kentucky or other big areas, we don't realize that they're right in our neighborhoods sometimes. Not giant caves, but sinkholes that can swallow streams and can divert water from the surface. So we have some big questions here, and we'd like to dabble and think that our monitors, that our SLs are helping us understand, first of all, monitoring the ups and downs, predicting, and then possibly making everybody feel a little better and in understanding. But first, a little history. Got an old map from 1884, and you can see Bucks County is a pretty clay-y place, Triassic clays and sandstones and shales. But right here we have the original Lowe's, and up here we have the original Home Depot, which is where the farmers would go to get some limestone or lime. That was the only place in town. But that history has given us essentially our problem, because right here is where the quarry is. Now, back in the day, all the streams around us still have trout, native browns. We had trout, as you can see, the primrose right here. And we have the karst topography, which we share with a very nice watershed right next to us, but divided by a fault line, which keeps our watersheds totally separate and groundwater separate, called the aqueduct. They have trout, lovely karst topography. We have karst topography, but we don't have trout. If you want to know where the carbonate rocks are in the state, check the map out. This is our little neck of the world. I know you folks are down in this section down here, so you've got a little bit going. And the maps here all show blue as being on the surface. Hopefully you don't have a lot of building. I should go back, but we'll look at Lancaster County a little later. In just a basic, the groundwater and carbonate rock, which is not permeable really until it develops fractures, joints, and bedding planes, which are enlarged by solution. The towns you may have heard of around Solebury, New Hope, Lahaska, Buckingham, and Doylestown all run along this side here, and Route 202 runs right up the gut here. Okay, so we know where the carbonate rock is. What it makes this a teachable moment is trying to give the students background with where the karst features are. And I was able to find a map, 2003, of karst features. Now, when you look at it, it's a lovely, colorful map. Purple means that there isn't any karst, it's urban development, and that's a good thing. It's where you have overlap, like the corridor here along the Pennsylvania Turnpike outside of Philly. And look at Lancaster County, my goodness, just loaded with this. But of course, we know it's a wonderful asset to the soil. So looking at art specifically, we're going to zoom in a little and try to make sense of this. What I'd like to show you is the scale basically is karst features count per 10 acres. And our Solebury count, this is as of 2003, shows us about 3 and 10 acres. Well, I'm telling you right now, this has jumped a big deal, and we'll take a look on the next one. So one more time, purple is urban impervious surface, and blue is rock on the surface, limestone carbonate or dolomite on the surface, but no development, no urban development. New Hope is good. Little bits of Lahaska have problems, and Buckingham has a little shopping center going on right here that has some issues. So you can see I've updated this to 2020 and put in an orange ring, which basically we have jumped from what they had 1 in 100 or 1 in 10 acres to 8, and we'll take a look at that in a minute. An overview of our Primrose Creek from the Delaware River right up here, this little blue thing, that's the Delaware River. And that's our outlet at Phillips Mill. And coming up here, we have the big gorilla in the chocolate factory, or whatever you want to call it, right here, the quarry, the school, and the post office. So we have the mill, the school, and the post office. It's just a cute little 17 tributary stream. A quick look at some geology. This is the quarry. Here is the school. And we have this 2 sections here. We have a fault and we have a dike running here. And these surrounding on this side, we have sandstone and we have shale. So the rocks that we're interested in is one, the Reichenbach dolomite and the Limeport limestone. And that's why the quarry is there. And taking a look at the same area, but with this out of, I got this off of a great app if you want. It's called Rocked, ROCKD, and it'll show you the basic geology of what's under you. But here you can see answers one of the questions to the kids. Well, I live up here. Is my house going to fall into a sinkhole? Or I live down here, and the answer is no. The solution is only occurring in this wedge here in the carbonate rocks. So, and it's confined. This is the Aquatong watershed over here, and ours is here. Okay. Thank you, Rachel, for upgrading our monitors. Thank you so much. And we have one above and one below, and they are down here at the mill. So we can watch what comes out of the quarry, and we watch what goes into the quarry, at least on the surface. And actually, there's been more not watching what's going into the quarry because of, well, as you'll see, sinkholes. So here we come to the first of 4 events for understanding. And event number 1 is this bad boy over here. And this is a year old. I have shown this at some of our other gatherings, but it gave us a beginning to sort of get a baseline on how these karst sinkholes developments happen in time. So April 12th of 2019, I should say that Shannon and David and helped put in the sensors back on May Day of 2018. So in that time, before this, we really didn't have too much going on, but then there was some other stuff going on that I'll get to. So thank you, SL158. All right, and what did it look like? Well, this is the old data screen that we had, but the blue line absolutely is a drop down to 0. This is our baseline. I'm sorry, this is the conductivity also dropping down here, but our baseline is about 20 centimeters during a normal run. Okay, so the Primrose main flow, you can hear them coming through Solbury School, and right here we have the pirated sinkhole, piratine sinkhole. Say within 100 yards of this. On the next 2 days later, combination of the staff of the school, they did some preliminary stopping, but you can see of the flow, of the sinkhole. And here we have the sinkhole that you just saw has enlarged from about 3 feet in diameter to about 10 feet in diameter, and a whole lot of depth going on here. So this is quite precarious right here. The throat, as it says, is waiting for tons of graded filter repair materials. And one of the points of this talk is to look at some of the remediation or the mitigation. And this is from the PennDOT. This is what you do if you have a small sinkhole less than 20 foot in diameter, but not near structures. So the one we just saw is perfect. This is your starting cost. And here's the recipe. Basically, you put big ones here, mediums and smaller, put a geotextile layer and cap it with a low permeability clay graded to promote drainage. Okay, a couple days later, looks like everything's good. Back to our new screen here, and we can see that the mean, it's April, and so our mean flow is running up in the high 200s and an occasional cloud buster right here. You can see the long term going on. So things look good, and that hasn't breached since, and that's the whole thing. Event number 2 is the man-made stressor, and this was recorded down here, down at Phillips Mill near the Delaware. This is water coming out of the quarry. And this is the complete opposite. No water left the quarry for 6 days, and it's a quarry failure to continue what they have to do. Leave, and this is what it looked like on our, from this time here, October 5th, all the way to October 10th or October. Actually, if you want to parse it, it really starts October 4th. Okay. So the cool thing was we had on October 13th scheduled a high school PTI test scheduled for this section of the creek. And I told the teacher, well, this is what the section looks like right now. And I said, but if they get it turned on, maybe something will happen, you know. So how are all those mayflies, stoneflies, caddisflies doing right now? I think they're holding their little breath. But we had a paradox, and it says it right here. After a week of zero flow, they found, look at these happy faces. They found so many bugs that it showed an excellent score. Anybody want to say why we wound up with an excellent score without water? Anybody want to speak up? Nope. Okay, because the leaf pack network is essentially all the bugs can hold their breath enough for the wet leaves save them. Okay, so moving on to event number 3. This is complete greed. 19 days, they're permitted in the quarry to pump 500,000 gallons a day. For 19 days, it exceeded 1.5 million. This is what it looks like according to our mayfly, our SL159. And we contacted the DEP about this somewhere about here, you know, maybe February 7th. So looking at this, February 7th, they were contacted, the DEP called them back, and you can see it finally got turned off here. But there were 3 more days that they were pumping us dry. And all this area here shows that there really wasn't a reason for them to do this, except for one thing. They wanted to go deeper and get more rock out of the bottom. And that was a bad thing and a no-no. It was breaking the contract of how deep they can go in the quarry to bring out their limestone. So let's focus at what happened in the good times, back in the old days, pre-quarry, with the water table. The water table looks fairly, this is just a model in 1926. That's 95 years ago. And here's where the quarry is going to be. And you can see in this, we're up to 2018 when we're starting to take results, and we get this cone of depression. Quarry literally, to make money, has to go deeper in the rock, pull out its materials, and keep the workers dry. You can't do this in scuba gear. So we were looking at how real is this cone of depression? Well, there was a study in 93, that's the latest I could find, potentiometric surface well map of Schriffler with a cone of depression. And here's our quarry right here. And these are the well heads that we know that along this, we have a cone of depression that runs on an axis for a mile here and a half a mile here. Okay, and these are the locations of the sinkholes in that. And keep in mind that from our geology map, this area over here is shale. Okay, so we're not going to get it below the quarry. But notice Solbury School is hammered. This state of California shape map, somewhat, it's all right, is looking at the quarry right now. The quarry has filled in and it has gotten bigger since this was taken, but we have sinkholes because we have something different than the other nearby watersheds, we have an active 95-year-old quarry. And I have to thank John Jackson for this, because he, in his first presentation on conductivity, thank you, John, the point is very simple, that what we have is an active quarry that is drastically dewatering the water table, allowing carbonic acid, the bad guy here, actually he's a good guy too, to rapidly recharge and dissolve the bedrock. If they left the water table alone, that wouldn't happen. So thank you, John. The litigation that we had basically was based on the hydrologic balance part. And this is something that, again, a lot of learning taking place, that water in the ground actually does support the over above features. And when it's removed, that pressure gone, things tend to follow the path of gravity. But the Pennsylvania Environmental Hearing Board, the EHB court, noted that the quarry had been digging deeper than it's permitted since permitted 120 feet since 2008. And here's a key thing, the DEP did nothing. And in their findings, they were also draining all the in-basin groundwater, so getting all this water out so they could get the rock out. The board strongly condemned the standard of review used by the DEP in its decision to permit the quarry to mine deeper, citing serious safety hazards to township residents, like the students of that school. This suit was brought by Solbury against New Hope Crushed Stone. It resulted in a fine of $8,000, which it's minuscule. The outlook right now is our water level is here. It needs to go to here. About we're about 55 feet needed to rise in the quarry before we get to a slowing down of dewatering. So predicting, whoops, I need to go back to here. This is a FEMA 100-year-old floodplain map that I got from the township's GIS portal. And you'll notice that along the creek, of course, is where the flooding is, but this is also the area of rapid exchange between the carbonic acid and the rock. So the last thing that I'm going to show you today is the event. And Solbury School, here's where our sensor is, SL158. Here's where this monster of a sinkhole opened up. But before we do that, I want to show you that we had a nice base flow going pretty much until June 1st, but nobody really knew. I was seeing this kind of pattern here, but you know, even my light didn't turn on until we started to get huge gaps in how low. And this rapid recharge dissolving cycle is sort of water in, water out, water in, water out, is constant and bringing rain and drain, I like to call it, mixed in with large storms like Isaias and other storms. We had a ton of them. That's why I put the whole map up here. But we have playground slumpage and the throat exposed, and that's going to come up next. That's the clue right there. And I hope the bugs are holding their breath. Here's poor old SL158. I remember when Dave hammered that into the ground right there, but there was a ton of water here. Here's the throat, 3 foot in diameter. This is the creek bed right up here at the school. And what we're going to do, we're at the Solbury School perspective. And I know you can't hear my today is September 1st. It's Tuesday. It's about 1:30, and we're looking at, from the deepest part of this sinkhole I've documented to another area that's under threat, and that is the playground. The playground is here. Closeness. Slumpage going and notice on the here slumpage being held up by the of the soil layers, only held up by the inner. Okay, the next day, after the maintenance guys poured cement and tons of earth down into here, I came back the next day. It was just an earth and cement uh, remediation. A couple weeks later, the school got a ton of riprap and threw it in there. But guess what? The cement and riprap failed. Right here. Another
riprap
downstream. Not much, but boy, oh boy, was that a lot of riprap. Tons and tons. So, professionally speaking, the school went and got a compaction grout company. And essentially, the way this works is they run a test hole and then they'll fill it from the bottom up. And they do a number of these. The machines for testing came in, but October was pretty busy with hurricanes. And after they put in
another one here,
the drills,
and another one
drilling in the
here,
shafts, put a cover on them to keep them
and then another
getting,
one here.
French,
And everything looks okay. The stream is moving
down yet.
swiftly by.
But there's a problem.
But there seems to be a problem, and we're going to take a look at this one. As you can see right here, the stream is flowing down into this hole, down into one of the drilled grout compaction shafts. So I'm certain that this is connecting. You can hear it. I'll stop talking.
Okay. On November 5th, they came back.
The area right here is where the sinkhole was. And you can see the shotcrete and the other grout finished. And you can see over here, pumping
routine. On a little later,
it's November 13th, we're at Silbury School.
13th of November.
At the site of the remediation. Looks like we're almost in the final stage of remediation. With the piping still here, just a little cleanup. Some of the injection molds,
these are the
guides
that
were left in the ground. So the
and one last
sediment did not fill the holes, and all the piping from the pressurized pumping here,
big stuff,
and the compressor
boys showed up here, and these trucks back
vehicle
here,
right back here.
Stuck. We have the compressor and
it's
then
just
the
a
high
little bit more.
pressurized ground.
It'll be done. So looks like.
Okay, and lastly, it was the day before Thanksgiving.
Well, here's where the sinkhole was, and now we have flow going on here, and a lot of overspilled grouting, making this look like a moonscape with the dozing that had taken place to level the slumpage. But we're at Silbury School. It's it's November 25th, the day before Thanksgiving. And it's nice to see that everything looks like it's a mess, but it's all back, and I believe until the next appearance of the sinkhole, which will happen inevitably, we have water flow going.
Okay, and looking back at our depth charts, we can see that we had bad times here, but we've had a pretty steady flow in at our sensor. So we're thankful for that. And that's it. Hopefully that's light at the end of the tunnel. Okay.
Wonderful. Thank you so much, Francis. That was really nice presentation, very informative.
Thank you.
We do have a question from Robert. Robert, if you want to ask that quick, and then we'll move on to John's presentation, and then we can do all the rest of questions at the end. Go ahead, Robert Sarnowski.
Question? Did I?
Oh, sorry, your hand was raised.
Oh, no, I'm sorry.
It was a clap.
A
It
clap,
was
yeah.
clapping.
Oh,
Oh, okay.
gotcha. Oh, I'm
Right.
sorry. That was a clap as opposed to a hand raise. Sorry. All right, let me just share my screen quick.
All right.
And there was Francis's introduction. There's Francis's.
Oh, yes, there he is.
There's his contact info if you happen to need it.
Right.
And now we have John Jackson doing part 2 of his conductivity and streams presentation. And I will stop share and let John take over with his presentation. Go ahead and share your screen, John.
All right, you got that, Stroud, opening slide?
Yes.
All right,
All good.
so I'm not going to go backwards, and everyone is more than welcome. What I did last time was talk about when you're measuring conductivity, what you're really doing. Try to take a bunch of ecology, geochemistry, water chemistry, and simplify it down into some bite-sized bits for you guys. Now I'm going to talk about the so what. What does it mean? How do you go from microsiemens per centimeter to something that translates into biology or is of ecological significance? And just a reminder, if and when you dive into this stuff, with your sensors, you're measuring electrical conductivity or specific conductance. You're hopefully measuring movement electricity compensated for temperature, 25C. It's really important that you make sure you use that temperature compensated measure. But if you dive into the literature, you're going to see references to salinity, to total dissolved solids, to salts, whether it's sodium, potassium, calcium, magnesium chlorides, or to chloride. These are all related. You could also add in here hardness. You could add in some degree of alkalinity. There's an immense amount of correlation, not all equal, but related. So a couple of things to remember. You're measuring salt. The salt could be sodium chloride. It could also be alkalinity. It could be calcium carbonate. In other words, limestone. That's part of your conductivity measure. Specific conductance doesn't tell you anything about what you're measuring, whether it's CaCO3, NaCl, MgCl2. They're all going to show up as ions letting electricity move, either faster or slower, more or less. Specific conductance varies naturally in response to precipitation. So you'll see lots of dilution events every time it rains, hopefully, unless it's in the winter, in which case you might see spikes. And we'll talk about that today. But naturally, what you see are dilutions. But you also can see a lot of geographic variation. And from my perspective, that geographic variation is more important than those short-term dilution spikes. And that's the last point. The natural spatial variation, that underlying geology signal, may be more important than natural temporal variation, the dilution events. There's not a lot of science on the dilution events. And believe it or not, there's not that much science on understanding the biological implications of the geologic signal. But from what we've done or what I've seen, there's a difference between low conductivity waters or soft waters, moderately hard waters, and hard waters. It affects the animals. So today, what we're going to do is talk about electrical conductivity as a measure of salt. We're going to talk about it as a physiological parameter. In other words, your ambient salt concentration affects the water balance and the ion balance inside the aquatic organism. There's this internal balance that you have and I have. One of the reasons why you have concerns when you get dehydrated is even as a human, your ion balance can get messed up, and that has serious health effects. And the last thing is these mechanisms of what we might refer to as salt toxicity. There's not a lot known about that, and it won't take a citizen asking you questions before you're going to run into an end of what you know. And part of that is because there's a lot that we don't know. The science isn't done. A couple of things about osmoregulation, maintaining your salt and water balance, that I think is helpful to keep in mind. So these are illustrations of when you grab red blood cells. You may have even done this in high school biology. When you put it in an isotonic solution, a solution where the ionic pressures are the same inside and outside the cell, so water in and water out is equal, and the cells look natural. You put it into a salty solution, what we would call a hypertonic solution, the cells shrink up, they shrivel up. It's very easy to see this. This is very easy to do, again, in the classroom, as long as you're willing to prick your finger. And that's just because the water on the outside of the cell, there's so much salt in it, it's sucking water out of the cell into the environment around it. That's what's happening when we're salting our environment. The reverse is true when you put the animal in a hypotonic solution, which would be like dropping an animal into low ionic strength water. What happens there is water rushes into the cell, and you can actually blow up your cells over time. This is a more graphic balance, and I'm not going to spend a lot of time on this, but I included it so that you could see that there's a water component and there's a salt. In this case, it's labeled as sodium component. So here's where your animal's internal body ionic set point is. You put it in salty water, and you have the movement of salts out of the animal and into the, let's reverse that. I think I did this in reverse. Let's see, hypotonic water out of, from the body to it's the other way around. I labeled this wrong. So we'll move on to this one. It's one I didn't do, and therefore it's right. This is an illustration of water movement and salt movement in and out of a salmonid. What we're trying to do, say rainbow trout. So you have a migratory fish that lives part of the time in fresh water, that's at the top, part of the time in salt water. These guys are unique in their ability to physiologically turn on and off water pumps and salt pumps. So when they're in fresh water, their big problem is a lot of water going in, and that means a lot of water needs to go out. At the same time, they're losing ions all over the place, and they need to conserve them. So they end up excreting what we would call a dilute urine. Conserve salts, dump your water. That same animal, as they migrate down to the ocean, needs to reverse that. And in this case, they're going to be losing water out of them, and but they're going to get salts moving in. And that means too much salt. So for them, they're going to excrete a concentrated urine where they're trying to save water and dump ions. That's what's happening in our environment as we salt it up. We're taking an animal that normally behaves like this, and we're asking them to make this move. And that's our problem. A rainbow trout evolved to make that migration. Eels, shad, they've all evolved to change from being a freshwater to a saltwater animal, and then reverse it. But most of our aquatic organisms don't have that ability, and that's where the stress comes. The surprising thing is salt is not like a pesticide. It's not horribly toxic, where it's micrograms of salt and you're killing things, or even nanograms. It takes milligrams of salt to make a difference, many-fold higher than is occurring naturally. So why are we concerned about it? You've all heard me talk about this. Why am I concerned about salt physiology? It's because our streams are becoming saltier. Everywhere where we have people dumping road salt, where we have wastewater streams, we're seeing increases in salt. The earliest study I was aware of was actually for the Schuylkill River, right at Philadelphia. It was water intake for Philadelphia, drinking water. And in this period of 73 to 99, 26 years, both chloride and sodium doubled in that time frame. After that, by 2005, you see a series of papers pumping out. Everybody who goes and looks, if they're lucky enough to have a long-term data, and in most cases, it's not as long. You know, this one starting in 85, this one starting in 83. This one goes back further into the late 60s, early 70s. But everywhere we're looking, we're seeing these increases. So this is Maryland, this is New York, this is New Hampshire, just as an example. And this has to do with this increase in salt applications, where what we're doing today in the 20 metric tons, this is total salt applications, rock salt in the United States from the 1940. And if I extend it out, I'm told today that somewhere we're around 23 million metric tons, more than double that was happening when the Clean Water Act occurred. And all of this is happening not because people are trying to damage the environment, but because safety and economics are asking for clearer roads, faster travel during the dead of winter. So when we started looking in streams, we started seeing salt showing up. And I noticed this back in the 2000s, but I didn't have the access to those long-term data that we have now. These are some base flow water chemistry from that Patty Haig, and I looked and I didn't see Patty on this call. She is a Westchester Master student, just finished up last week, and she's also a Chester County Master Watershed Steward. And these are just grab samples from the sites that she installed sensors on. A couple of things to note. First of all, this is late summer. There hasn't been a salt application in months. September 22nd, 2019. Just as a comparison, White Clay Creek at the Stroud Center, which is a limestone influenced stream, its background conductivity is 235. It's way down here compared to 1600. It's less than half of every sample of 5 different streams around Westchester Borough in Chester County, PA. So all 5 streams we sampled that are draining an urban center, Westchester, had far more higher conductivity than we ever see in White Clay Creek. The other thing I plotted here, it's an old standard, but it's a standard EPA developed in 1988. It's a chloride standard that's a chronic standard that represents what they said was a 4-day exposure once every 3 years. This is background. This is day after day after day. 2 cases exceeding the standard, 2 other cases very close to the standard. Those of you who've been looking at your data, where you have some winter inputs, you have to realize that there's also a lot of temporal variability. And with the temporal variability, sometimes we get focused on those peaks. So these are data out of Delaware at First State National Historic Park. This is being run by the TNC stream stewards down in First State. And they are, have been running the sensors now for quite a while. They also have the headwaters of these streams are highly urbanized. And they have seen peaks over 40,000, approaching 45,000, just like we've seen around Westchester Borough. I averaged those every 5-minute measures to 96-hour running averages. And so instead of being up 40,000, we're up still at the 20,000. Seawater is at 55,000, just for comparison. So this site at times peaks very close to seawater, to ocean water. That's temporal variability, but remember, we have this other measure down here, 500, 700, 900, 1,000, That's that base flow for months and months and months. The next series of slides are going to be results from toxicity tests. And what I've done in a toxicity test is taken an animal and exposed them to increasing chloride concentrations and looked at whether they survive or die. And based on this, what we refer to as a dose response curve, one of the common ways of interpreting this is cutting it right in the middle. What's the concentration where you kill 50% of your animals? Very simple, LC50 it's called. It's not a protective level. At this LC50, you've killed half of your individuals. That's nowhere close to being protective. But those are the numbers I'm showing you just as a starting point. The first thing I want to show you is that hardness matters, or your background water chemistry matters. So these are 3 streams in the Eastern PA that vary in conductivity from moderately hard to soft water. These are the LC50s. This is the amount of salt it took to kill 50% of this mayfly. Its name has changed, Neocloeon triangulifera. It's a common mayfly. We find it throughout Eastern North America, including in Pennsylvania. So when you have moderately hard, that hardness is protective. So it takes more salt to kill them than in a softer or very soft water. So hardness matters. The softer the water, the more toxic your chloride, or the more toxic your salt. It's, if I slip up, don't let me. In many cases, and you'll see this in a moment, we may talk about chloride, but right now the science is saying it's not the chloride that's toxic. It's either salt in general, or it's the cation. Is it sodium? Is it magnesium? Is it calcium? Is it potassium? This is the second thing I want to show you, is not all species are sensitive. So these are a series of fish, of some common lab animals that we use, Daphnia and Daphnia magna, as well as some mayflies that we've used in the lab. There's an 80% difference between the most tolerant, in this case, rainbow trout, and our most sensitive mayfly in a short 2-day lethal exposure. That's a huge amount. So you can have rainbow trout happy in a stream that might be killing mayflies. Third thing, exposure matters. This is the LC50s expressed as chloride for this single mayfly, Centroptilum triangulifera. The difference is 2-day exposure or a 30-day exposure, which in this animal at 25 degrees or 20 degrees C, this is about a single life cycle in the summer. So this would be like running a summer bioassay. If it was only a 2-day spike, you'd sit in here at 2,500 versus at 500, 75% reduction. Another thing you have to pay attention is temperature. Toxicity of chloride increases with increasing temperature. So when it's cold, the animals can tolerate a lot more chloride or a lot more salt than they can when it's cold. So we ran tests from 5 to 25. Most streams don't get up to 25, but they can commonly get to 20 around here, and they certainly get down to 5. And this is one of the reasons I pay less attention to these spikes, is because the chloride is less toxic than these summer temperatures, where that base flow salt is just banging away and stressing the animals day in and day out for months on end. And this is what that means when you take that spike data as an acute test, but I plotted 2 lines here. One is the acute toxicity at 5 degrees versus 20 degrees. At 20 degrees, this site would have had 21 days where we would have surpassed the LC50. But based on the LC50 at 5 degrees, we only had 2 days. Still toxic, so the spike was meaningful, but there's a big difference between having 21 days versus 2 days at the toxic limit. That's why temperature matters, and that's why you need to pay attention to what your summer concentrations are, as well as what your winter concentrations are. I didn't plot the acute concentrations, but the acute concentrations down here are going to be quite similar, because remember, your temperatures are warmer and you have this long exposure, not brief little spikes. Last thing, not all salts are equal. This is acute toxicity data, 48-hour tests, standard lab animals looking at sodium chloride, magnesium chloride, calcium chloride, all three common de-icing salts. You notice these are LC50s, so the lower the number, the more toxic it is. For this fish and these two daphniids, magnesium chloride is clearly more toxic than sodium chloride or calcium chloride. The other thing that jumps out is the calcium chloride can be equal, might be more toxic, might be less toxic. It depends on the animal. We get three different responses here, depending on Ceredaphnia, Daphnia magna, and mud minnow. Another way of looking at it, again, not all species are equal. This is magnesium chloride, sodium chloride, calcium chloride. This is rainbow trout growth, 25 days. So this is a chronic exposure, not an acute exposure. For this animal, for 25 days, magnesium chloride, increasing concentration here, didn't affect growth, whereas sodium chloride decreased growth and calcium chloride decreased growth. In fact, calcium chloride decreased growth more. The funny thing in all of this, and this is one of our challenges, is for this fish, rainbow trout, magnesium chloride would be the least negative, the least stressful, the least toxic salt. But if we looked at the previous slide, magnesium chloride was the worst. This is one of our challenges. How do we digest that? And that's one of the reasons you're not seeing definitive salt standards right now, is as we're collecting data, we're trying to digest toxicity versus osmotic stress. So sodium chloride seems to be, in many cases, behaving osmotically, messing up the water balance. Magnesium chloride, calcium chloride, potassium chloride, that cation is having a different interaction. But here's what we do know, is conductivity correlates with degradation. So this is a macroinvertebrate score I often use, where 0 is horrible and 20 is great. These are straight out of the Schuylkill River Basin. And here's our conductivities. And it's a pretty nice regression. As conductivity goes up, your bugs get worse and worse. But remember, correlation may not equal causation. This data was the first thing that highlighted that maybe we have something going on with salt. But remember, look at, these are base flow March samples, April samples, and we're not above 600. We have many sites that are beyond 600 at this point in terms of base flow, as in 11, 12, 1300. So what else is going on? One of the things to remember, and a tool to use when you're talking about conductivity, is it illustrates the connection between people and water. In other words, we apply road salt to the ground, to the hard surfaces, and it ends up going directly to the stream quickly by way of the pipes, and then later by way of groundwater contamination, it continues to migrate to the stream. So that's why we have salt in the summer and salt in the winter. Well, what else is going on? We have oils, metals, asphalt sealants, herbicides, insecticides, soaps, drugs, personal care products, fertilizers. All these things are making their way, whether it's by way of a storm drain, by way of a sewage treatment plant, by way of runoff from your front yard or out of your septic system. They're all going in the way of a chemical cocktail. And the freshwater salinization syndrome is really just a measure of saying, yes, we have a lot of salt, but we also have a whole lot of other things too. At this point, yes, we have streams that have salt toxicity issues, but it doesn't mean it's their only issue. There are other concerns out there, other pollutants that we didn't pay attention to when the Clean Water Act was passed, we didn't pay attention to them before some science came out. So we started paying attention to de-icing salts in the early 2000s. About the same time, the city of Austin noticed that PAHs from coal-derived sealants was toxic to gammas, was toxic to aquatic animals. And USGS ran with that. And now there's a lot of science pointing their finger at PAHs from asphalt sealants that are derived from coal. Something that came out in the last month, though, you may or may not know about, is there's now some new science that says there's another stressor coming off of the roadway, and one we never paid attention to. PPD comes out of the tires. It's part of the process of making road tires. They're found it in streams, and they found it to be quite toxic to migratory salmon. This was a study out of either Oregon or Washington, out a couple weeks ago. I don't think this is anything new. I think this is a progression and shows the complexity. So be careful about pointing your finger at salt when we know there's these other things going on. So I'm always asked, well, what's of concern? This is just LC50s from mayflies expressed as conductivity or chloride. But remember, if you're working with conductivity, you need to know what you started with. What was your background? Was it 100? Was it 200? Was it 250? Was it 500? Do you have a lot of limestone or not? Because your limestone changes the toxicity of your salts. But based on bioassays we've run in using White Clay Creek water, so moderately hard water at 20 degrees, we've seen acute toxicities for mayflies in the 300 to 3,000 range, and chronic toxicities in the 150 to 900 range. And that translates for our water in 1,000 to 8,500 for conductivity, and for background or long-term exposures, say 500 to 2,500, in that range. So if you're seeing those kinds of numbers, that to me suggests you might have chlorides that are high enough or salts that are high enough to be toxic. So points to remember: salt's increasing, especially in urban streams. We're seeing it everywhere. We see it in the summer, we see it in the winter. Those elevated salts can cause physiological stress. They may even be toxic. So as soon as we start salting things, we see a change in growth rates, for example. The brief spikes in the winter are not well understood. We haven't run a lot of bioassays at 5 degrees. And we haven't run a lot of bioassays where it varies and the exposure may be less than, say, 4 days. It may be only 12 hours or something like that. That's just not been done, and I can't tell you what it means. It doesn't make them happy, but I can't tell you that it's gonna kill them. The last thing is the impact of the salt. Keep this in mind. This is why it's so hard to generalize. It depends on the salt concentration. It depends on your background stream hardness. In other words, your underlying geology. It depends on the exposure time. It depends on the types of salts that are being applied. It depends on water temperature, so season. And finally, it depends on the species that you have. So that's what I have for you.
Excellent. Thank you, John. Can you take off screen share then?
Yep, I'm looking for it.
Yeah.
There we go.
Okay. I am going to share my screen. Thank you very much, John. An excellent presentation as expected. I am going to share my screen. Actually, so we're going to do 2 polls now. So if everyone can just stay on to the call for these 2 polls, it would be very much appreciated. So I'm going to launch this poll right now via Zoom. So if everyone could take a few minutes to just fill this out. So you should be viewing the poll now. So if you could just fill that out, that would be very much appreciated.
And I'll stick around for questions after you get through the polls.
Great, great. Okay, we're gone. We've got quite a few. It's gone up, up, up. Good, good. Okay, we've got almost complete, 72%. Is everyone seeing? The poll? Anyone not seeing the poll? Looks like we're about topped out. So I will end polling now. Okay. And then here I can share results. So it looks like the depth of information was good and most people found the presentations useful. So that's good. So I'm going to stop these results and then I'm going to copy a link into the chat box. And if everyone could take that link and copy it out and put it into your search engine, Google or whatever, and fill that out. They're open-ended, so I'll leave a couple minutes to do this. They don't have to be extensive, but that everyone should just open up your chat and you should see that link there. So just copy. You can't click on that in the chat, so you're going to need to just copy that out and paste it into your Google or something. And Rachel just posted it as well, Rachel Becker Klein. So if you could just take a couple minutes to fill that out, that would be very much appreciated as well. And we'll just, I'll bring up my screen to share John's information again while we wait.
Dave, if you want, as people start responding, I can share my screen so they can see that word cloud. But so far, nothing yet.
Sure, that'd be great, Rachel. Rachel is helping Stroud do some of these polling type things, among other things. Cool. Do you have a tally, Rachel, of how many people are completing it?
Let's see. I don't see a tally, but why don't we give people another like 20 seconds and then we'll put one more question up.
Okay. Pretty neat feature here.
Cool. All right, so we'll do 2 more seconds and then I'm going to, so hit submit if you didn't hit submit yet. And then I'm going to do our next one, which will hopefully come up. Let's see. I'm going to switch to this. Hopefully folks are seeing this next poll. Are you seeing it, Dave?
I'm saying no responses received yet.
Right.
Yeah. There are some results are showing up. Help, salt.
Papers. Okay, and then I think we'll do 30 more seconds here too. So I appreciate you guys staying a little extra to do this. Thank you.
Geology. Information.
Mm.
Cool.
All right. If you did not hit submit yet, go ahead and hit submit. And thank you very much.
Wonderful. All right. Thanks, everyone. I'm going to go back to sharing. Well, actually, why don't we just do, I'm not even going to go into the rest of my slides. Why don't we just address any questions that we might have for Francis or John Jackson? Any questions from anyone?
There's one in the chat that I can answer easily. In part, and this is a really good one, a lot of people don't realize trout, whether it's rainbow trout or brook trout, they tend to be surface feeders. That's why fly fishing works so well. And so in many cases where you have a healthy riparian forest, your trout are surviving on terrestrial insects. And if you go into the acid mine drainage areas where they've remediated some of the acidity so that brook trout can still live, or acid rain areas that have been remediated to the point that brook trout can still live, there can be brook trout everywhere and the bugs are decimated. And it's because they're feeding on terrestrial insects. So they're opportunists. They can feed in the drift or they can feed on the surface. And if the drift is, the bugs in the water are not as happy, then the forest may provide them what they need.
Great. Francis, actually, I think, Francis, you're still there. Good. There's a question about what is the link to the geological website that was discussed in the presentation? Can you put that link into the chat, Francis? I think, are you John Barbas, are you talking about the Rocked website?
Yes.
Okay, Francis, you're muted. Okay, so maybe Francis will post that in there. Let's see. Here's John, there's a question in the chat from Carol Armstrong. The baseline conductivity in Valley Creek and East Whiteland is at least 800 microsiemens per centimeter, but this stream supports brown trout. Would you hypothesize the hardness of the water is protecting the trout from the high salt peaks and probably high chronic levels of salt?
Yes.
Simply put, Valley Creek is a superior limestone stream with a whole lot of buffering capacity from all that ridiculousness in terms of urbanization surrounding it.
What Valley Creek does have, see, this is one of the tricky things about focusing on a single species. The brown trout are doing relatively well, or have been. They have a temperature issue at this point for sure. And they probably would be a little happier if they weren't getting salted. But the high alkalinity waters and limestone streams in general naturally have more depauperate faunas, fewer bugs. They've been very challenging to describe the reference condition because we don't have a lot of reference sites, but also that background alkalinity, when it gets that high, it's eliminating taxa naturally. So people who've ever looked at a natural limestone stream quite often will see far fewer species than we would see in a moderately hard system. And that's just because that they're having to balance their salts and waters every day, 24/7, 365. And it's a bit of work. And so there, for Pennsylvania, for example, there's a different index used to assess limestone streams. And that's used only on the pure limestone streams, the really high alkalinity streams.
Okay, let's see here. Here's another one from Carol for Francis. Francis, does the DEP enforce the practices used for responding to sinkholes on private land? Is the DEP the first line of communication when a private sinkhole is found before any action is taken?
Now, I am not an expert on this. I only have a small pond to kind of watch over. I would say a call to the DEP would definitely get you on track, whether they're the first. They definitely should be in the loop, because how else would my map get the map of all the karst problems ever be updated? You know what I mean? So
Here's what I would say. Can I add something to this,
Yes.
Francis?
Sure.
I would go, first of all, to fish and boat. And the reason why I go to fish and boat is because if you have dead fish, you have an immediate enforcement action. If you had a trout stream where you had dead trout, they're even going to be that much more aggressive. Your second approach then is to your watershed coordinator with PADEP, or to one of the emergency call lines to report the loss. The third would be, and this is the one I don't know about, and it's been happening so much around the Mariner East pipeline, but somewhere in the mining division, there's probably an emergency call line for sinkhole development. I would call all three and hope somebody, but I'll be honest with you, fish and boat is really responsive.
yes.
And they also have enforcement powers in terms of fines that get involved right away, but they need to be there right when it happens. They need to find dead
Yes.
fish.
Right.
Excellent.
Thank you, John.
Kevin Morrissey.
Yeah, I would just, well, one, I would like to add that I'm a Salisbury resident and have been involved with Primrose Creek for a while. And I just would like to thank Francis for his doggedly monitoring energy of the creek. You know, there've been times when it's been raining or it's been just generally miserable outside, and I get a text from him. You know, he's out there. So I just really would like to thank his efforts for all of that. And if now I also could add, we've had some success with the mining department. A quarry is a well, again, if there is a mine there, if there's a sinkhole and it's near a mining activity, the mining department is involved in this whole process as well, and I'd like to suggest they should be contacted along with the other sources that have been indicated.
Great, thank you, Kevin. And agreed. Francis is a really good example of someone who just has a real personal pulse on the on the whole watershed, and has really clearly spent years developing his understanding of all the details going on there. So thank you again, Francis, for that presentation.
Okay.
Anyone else here with questions or comments for John or Francis or anything else on the radar?
Yeah, Dave, I have my usual favorite subject, the 2G to 4G transition. Maybe at some point we could say, you know, when is 2G going away? I keep hearing different stories about it. We got a lot of stations out there operating on 2G, but I was told, or somebody said, it's really not going to end in December, which is a couple of weeks from now. So,
well, Shannon, do you want to comment on that?
Yeah, there's still no definitive word that it is going to happen, but you've got all the hardware, or you should be in the process of upgrading your stations. There's only a few of our stations out there that need the upgrade, and we were actually out of stock of 4G boards, so we were waiting for a new shipment to come in. So we'll be getting most of ours either ready to go or completed by the end of the year, and if not, it will just respond as things turn off. But I don't think there's going to be something happen right at midnight on New Year's Eve like it did a few years ago when AT&T turned off their 2G service. But just in case everybody's stations do turn off on January 1st, we'll know. But yeah, T-Mobile hasn't officially said they're turning it off because of all sorts of logistical issues that have happened in the last year. So it may not be as urgent a need to replace them by New Year's like it was a few years ago.
Oh, okay. Thanks, Shannon. And thanks to you and Sarah for getting me on course. I actually upgraded one of my sensor stations relatively painlessly. I was quite surprised. Usually it doesn't work the first time, but it was relatively straightforward. So what you're saying is the modems are in short supply at this point.
No, they're not in short supply, but we've used up, we've bought like over 100 of them in the last, less than a year, I guess, replacing all of our stations. So we just have been going through them a lot quicker than we used to be. And we are also including them in the monitoring kit stations that we're selling online now. So we've got to have inventory for those. So some of the stations that need the 4G upgrade are up in New Jersey, like the couple up in Newton. And I think Christine's on there, and a few of the other folks that we just, due to travel logistics, well, right now with snowstorms and everything, we can't do that. But we were also trying to limit our out-of-state technical support trips until some of the COVID restrictions were eased up on. So we'll be making bigger, longer road trips to some of our other remote stations to do those upgrades. But at this point, yeah, we're just waiting for another box to come in. And when we order parts and pieces, sometimes it's taking several weeks to a month or more for things to come in because of all the vendors having shipping issues and everything else. So it's just kind of lots of things to juggle around on our end.
Dave, I have a quick question for Francis.
It looks like Francis took a call.
Oh, okay. Well, I'll ask you the question. That problem in Primrose Creek is it's a carbonate aquifer, right?
Mm.
Would you be able to simulate that problem if you had heavy water mining? Forget about the quarry, but if you just had a lot of those are popular aquifers to pump water out for city water.
Yeah, we actually had it.
Could that be a problem?
Yeah, very, very much so. I know the township had been approached by a freshwater company to possibly do what you're just saying. And I think the answer was no, because essentially the same problem would be occurring. You'd be mining the water,
dropping the water table
dropping the water table and carrying on a problem. That would be a disaster if that happened. Thank you for that question.
Yeah, because we're dealing with that, something similar to that actually in the next few years down here in Southeast Pennsylvania. And right now everything is nice because there's no well, but if it begins to drop the water table, very large rain events could then begin to start to create sinkholes.
Yeah.
If I could add, and of course, each environment is different and you can't compare it with your situation, but in the Primrose, on average, they were going somewhere around about 1.5 million gallons a day. And in peak storm situations, they would go up to 4 or 5 million.
Yeah, there's the same numbers. We have the same size watershed and the same kind of numbers you're talking about.
Yeah. Okay. Well,
yeah,
that's the problem that's occurring or was occurring. The quarry is out of business. As of about less than a year ago.
Yeah. Thank you.
Thank you.
Okay. Anything from anyone else? All good?
All good.
We are at 3:54, so we've had quite a meeting today. All right, well, if there's no other questions, I guess we can just sign off, and I'll wish everyone a happy holidays and happy new year and all, and be safe out there. Take care, and happy new year.
Okay. See you later, Dave.
Bye all.
Bye-bye.
Success.
Yeah, thanks, Francis.
You want to
Oh,
stop
thank you.
recording, Dave?
Zach and Susan are still on. Zach or Susan, do you have any other questions or anything? Maybe they stepped aside.
Dave, do you want to stop the recording?
Oh, yeah, thanks, Shannon.
Paul.
Stopping recording.